Dear participants, today is the day 5, the session 9, and we are having two sessions. So, this is our first session of today. The session 9, it will be taken by Dr. Ravindra sir, and the topic is flood disaster reduction strategies. So, we are delighted to welcome Ravindra sir, who is a scientist at Surface Water Hydrology Division, National Institute of Hydrology, Roorkee. So, sir has did graduation in agricultural engineering from Mahatma Phule Krishi Vidyapith, Rahuri, Maharashtra, and Master of Technology in Agricultural Engineering with specialization in Irrigation and Drainage Engineering from the Department of Irrigation and Drainage Engineering, College of Technology, GB Pant University of Agriculture Technology, Uttarakhand. Sir has also received the PhD degree in the field of hydrological modeling from the Department of Hydrology, IIT Roorkee in 2010. So Sir has served Western Himalayan Regional Center NIA Jammu from April 2016 to August 2022. So during his service tenure, he has attended more than 50 training courses organized by various reputed academic and central government institutions in India. So joining NIH as scientist B in 2010, he has over 15 years of experience in hydrology and hydraulics, dealing with the surface water assessment, conceptual and remote sensing approaches, irrigation, integrated water resource management, spring hydrology, disaster risk assessment and management, soft computing techniques in hydrology, and many more fields. So, Sir has published more than 38 research papers in international and national journals and conferences, and Sir is associated with the conduction of 14 training programs, workshops, symposia, brainstorming sessions at the national level. Sir, we are privileged to welcome you, sir, with us today, and would like to express our gratitude for your valuable time, sir.
Okay, thank you very much, Professor Sudhanta, for giving my introduction. And one more thing I want to add, I did also second master in disaster management policy from
Yes.
GRIPS, Japan. It is in disaster management policy for related disaster. So I get polished after getting this master training at Japan, because Japan is leader in disaster management.
Yes.
So I got some field experience at Japan. So I want to share that experience with you. And first of all, I am very much thankful to you and all faculty members from NIT Trichy for providing me opportunity to reach out different participant of this training course. I hope that participant will get some new concept from this my lecture. I try to keep my presentation in mostly general form, so that most of the aspect of flood disaster management related to flood will be imparted to participants. So with this brief introduction, I welcome all of you, and I start my presentation on flood disaster risk reduction strategies. My presentation is visible?
Yes, sir. It is visible.
Okay.
Yeah.
So in this presentation, we will discuss flood remain India's most frequent large-scale disaster, affecting millions annually with significant loss of life and economic damage across major river basins. This desk contains official India flood map sources, 3 detailed case studies, then technical advances in monitoring, SAR, machine learning, and GLOPAS, and a practical implementation roadmap, then hydrological hydraulic modeling studies, few case studies conducted by us, then flood disaster management framework in general, and then outcome will be enhanced situational awareness, improved early warning systems, risk-informed reservoir operations, and targeted mitigation strategy to reduce vulnerability in high-risk zones. So this is a bit background of this talk. As we know, India is the worst flood-affected country in the world after Bangladesh, which accounts for 1/5 of global death count due to floods. That is information by Dartmouth Flood Observatory database. This is a global database, and this chart shows the economical losses due to natural disasters in India. But there is United Nations DRR program is there. they highly object to call it natural disaster because when there is vulnerability get combined with hazard, then it become disasters. So they are insisting do not call it is a natural disasters, call it is a disasters only because risk is associated with hazard and vulnerability. So if we look at economic losses due to this disaster, we are getting so much losses from this is chart showing disaster losses from 1998 to 2022, and here also more than earthquake Mumbai flood cost lot of loss. Then Uttarakhand floods, South Indian floods. Then is a cyclone recently cyclone flood, and this chart shows from 1998 to 2022. And India's highest uninsured economic loss was in 2014 at cost of $15.18 billion due to cyclone Hudhud and the Jammu Kashmir floods. So I am providing this case study of Jammu Kashmir flood of 2014 in this my talk. Then we will why flood matter in India, because as I told, there is a high exposure, dense population in floodplains plus monsoon dominated rainfall pattern that and high exposure leads to high risk in flood disaster due to flood disaster. As we know, over 40 million hectares, that is 12% of land, is flood prone in India. 70% of annual rainfall occurs during monsoon season, that is during June to September. And these, what are the main drivers of flood types? There is a multi-hazard mechanism requires tailored solution. And in India, we face different flood types like riverine flood, flash floods, urban fluvial floods, coastal surge, and dam and embankment failures. And then there is another factor recently get added into this, that is climate change intensification. What is it? It is increasing extreme rainfall event and sea level rise. So increasing extreme rainfall event and sea level rise, these are most important factors which are going to affect flood inundated area, and it is going to affect the risk of flood in India. As per IPCC projection, which indicate 10 to 20% increase in monsoon precipitation intensity and higher frequency of cyclonic storm by 2050. So these are different type. Mostly we consider that is fluvial. Fluvial is due to rainfall, and fluvial is due to rainfall and man-made structure. Then there is cyclonic flooding and tidal flooding. So all these type we will see different case studies here. So what is flash flood? Because it is one of the danger type of flood. Because in this case of flash flooding, we get very less time for preparedness. So we required some flood alert system for such kind of flood, because what is flash flood? When flooding that begins within 6 hours or often within 3 hours of the heavy rainfall, that we call flash flood. Flash flood can be caused most often due to extremely heavy rainfall from thunderstorms or dam or levee breaks or mudslides, that is debris flow. The intensity of rainfall, the location and distribution of rainfall, and the land use and topography, vegetation types, growth, density, soil type, and soil water content all determine just how quickly the flash flooding may occur and influence where it may occur. Then there is another type of most important flood is urban flooding, and it occur mostly in urban area, are prone to flooding in short time span. Then flash flooding occurs so quickly that people are caught off guard, and it becomes dangerous if they encounter high fast moving water while traveling. So these are different based on these flood types. We must have some different flood management approaches. We require, in case of flash flood, we require stream flow forecasting. That is most efficient early warning system for flash flood. Then extreme event and prediction of forecasting, that is WRF model kind thing, or different rainfall spell. We can use such a methodology to estimate extreme event and prediction or forecasting at smaller scale. Because at India scale, we having forecasting at 12 kilometer grid size, but now IITM Institute, they are trying to provide this extreme event by using WRF model, giving forecast at 3 kilometer or 6 kilometer grid size. So that is a new advancement. Then because mostly we ignore reservoir operation, but in case of flood of 2018 Kerala flood, in that case, it is seen that reservoir operation is one of the most important factors that can cause that by managing this reservoir operation very well, we can reduce flood risk in advance also. So reservoir operation is one of the most important part of this flood risk management. Then flood planning, para engine, and then there is another thing, we can use vulnerability mapping, and we can incorporate climate change. So this is the flood management approach we can use. Then this is a disaster impact from 1980 to 2019, and it is seen that after 2000 there is a very high increase in flood disaster in case of your economic losses and losses of lives also. So this is a flood prone area in India and damages in year 2020, and these are different floods starting from 2000, that is Kedarnath flood of 2013 is one of the biggest flood in India that happened in 2013, because a lot of people die in this flood. Then as I told, Jammu Kashmir flood of September 2014, then Mumbai flood, Gujarat flood, Kerala flood, Chennai flood of 2015, then Odisha flood of 2011, Odisha flood of 2018, Krishna flood of 2019 and 2009 and 2019, Assam flood of 2020. So these are the state-wise deaths due to flood disaster in 2020. So in 2020, West Bengal shows highest death due to flood disaster, and in case of Nagaland, there is minimum number of deaths. And how in which state how many deaths is presented in this chart. So in 2020, extreme monsoon rains in India caused floods and landslides. Between June to October, extreme event caused at least 2,000 deaths and damages amounting to approximately 73,000 crore rupees. Then this is the disaster event in India from 1995 to 2015. So compared to all other disasters in India, the damages, economical damages due to the flood is very highest, and you can reveal from this chart. And according to the data presented in the Rajya Sabha in 2018, India lost 1,880 lives and suffered loss worth an estimated rupees 957 billion, that is rupees 95,000 crores due to flood across the country. Government data shows that between 1953 and 2011, on an average, floods claimed on an average 1,600 lives every year and caused losses including the houses, public property, and crop damages amounting rupees 36 billion, that is rupees 3,600 crores every year. So this is economical losses in crores due to flood disaster between 2010 and 2025. So Himachal, Uttarakhand, then Assam and Northeast region, they have highest number of flood disaster occurring. Then Maharashtra, Gujarat, Kerala, Chennai, and Odisha, this part having Even in Rajasthan also, flood disaster are increasing. So we will see in next 3-4 slides major floods in India during 2010 and 2025. So this is the major flood event timeline between 2010 and 2025. So major flood occurred 2010. This is major flood that occurred in Leh Ladakh, and it is due to cloudburst or flash flood. And around more than 10,000 people affected, and economic losses was 5,500 crores. Then flood of 2013, that is Uttarakhand flood, around 5,700 people died during this flood, and more than 1,10,000 people affected due to these floods. And we have experienced the losses during that 2013, and around 3,000 crore rupees, more than 3,000 crore rupees economic losses caused in Uttarakhand only. Then Chennai flood of 2015, that is a case of urban flooding, and in this flooding of 2015, more than 500 people have died, and 4.8 million people affected. And here we can see one thing clear, that when there is a flood affecting in mountainous area, there is less number of death or less number of people affected. But in case of urban flooding, large number of people get affected due to this flood, and economical losses is very higher. That is, in case of Chennai 2015 flood, around 20,000 crore rupees we got economical losses. So this is one of the most important thing. We must address urban flooding problem, because there is very large number of people get affected, and economical losses are very large. Then in case of 2018 Kerala flood, it is a case of extreme rainfall flood type, and in this case around 489 people lost their lives, and around 1 million people get affected due to this flood, and economical losses was around 26,000 crore rupees. And in 2022 in Assam floods, around we lost people affected are 5 million, more than 5 million, and economical loss was around 10,000 crores. So and this chart also shows number of floods up to 2025. Last year also we experienced very large flood in Punjab and Uttarakhand, and it is a case of monsoon flooding, and around 150 people dead last year. We lost 150 people due to flood last year in Punjab and Uttarakhand, and around 1 million people get affected, and loss was around 5,000 crores. And from this chart, you can see one thing, that because we are now using more technologies, so we are able to reduce our economical losses. But still, day by day, due to climate change and another factor, our challenges are increasing. So we require new technology. So understanding this thing, we require such a statistic. And this table also check different government sources. I have taken this data, and these are different sources to take these different losses. And if completely analyze different floods between 2010 to 2025, then we can get there are 21 major flood events, because this 21 major flood means there is 1,000 crore of economic losses we call, and more than 10,000 total death occurred in these flood events, and around 50 more than 50 million people get affected, and economical losses was around 1.5 lakh crore economical losses we caused during this 2010 to 2025. And these are the different states where more this flood event occurred. Assam top this list. In Assam, there are 5 events occurred. In Uttarakhand, 4 events. Maharashtra, 4 events. Tamil Nadu, 2 events. Bihar, 3 events. Kerala, 1 major event. Odisha, major 1 event. Jammu Kashmir, 1 major event. Himachal, 1 major event. And Punjab, 1 major event. So if we take look human casualty by years, then because I already told that in Uttarakhand flood we lost a large number of people, but recently we have large number of economical losses. We are able to reduce our number of death due to this flood, but economical losses are increasing. Then trend analysis shows that while individual events vary, urban flooding shows increasing casualty pattern. So this is one of the most important observations from this statistical data. Then we will see what are the recommended India flood map. That is national official map. So that NRC flood affected area atlas on one website, which gives historic and near real-time inundation map with satellite derived product. So you can go this website, and you will get such a high resolution satellite image showing the flood inundation area for the historical floods. That is important for policymakers and for researchers also to get historical data to calibrate and validate hydrologic or hydraulic models. Then there is recently on one website, they have developed this special flood early warning system, and presently they have developed for Godavari and Tapi river basin. And in this model, it is not satellite-based system, but they have used Mike 11 system to get flood inundation map and flood depth. So it is very advanced system. And in this system, also we get reservoir information, how much there is inflow to the reservoir and outflow to the reservoirs, and observation from CWC in real time. So now CWC and all other organizations, they are developing this methodology to cover all major basin of India. So this is one of the important website. You can check this website. Then recommended India flood map is operational gauge based forecast given by CWC as a national flood forecasting network. And presently, flood monitoring in India provided by Central Water Commission, which provides statistical methodology gauge-to-gauge correlation based on short-range flood forecast. Presently, flood forecasts are issued by CWC at 332 stations, out of which 133 inflow forecast stations and 199 level forecast stations. Annually, about 10,000 flood forecasts are issued by CWC, and you can check this website. Professor Sushanta, I am audible, na? Hello.
Yes, sir, you are audible, sir.
If there is any problem, please tell me. I am not getting anything. Okay.
Sure. Please go ahead, sir.
And there is another flood map. This is a flood forecast web page by Central Water Commission, and you can check this web page. And here you can get base stations, then level stations, inflow forecast station, abnormal flood, severe flood, extreme floods, and forecast available for inflow forecast station. So you can check this website also. Then there is one Google-based website is there, and here you can get some extreme warning, like extreme warning, danger warning, and other alert also you can get here. And for selected station, you can check where is the water level. at that specific gauge based on that CWC flood forecasting. So these websites are very much important during monsoon season, and every person know this site so that they can get a warning level in real time. Then this is global, that is GLOFAS, global flood warning system. It is as basic scale alert and forecast up to 30 days in advance. But it is this website we can use for synoptic view. Just 1 minute. Alexa, stop. Hello. So after this available website, now we will try to study the different causes of different floods. So I presented here one case study of Kerala flood that happened in 2018. And what is the key fact given by CWC and IMD? As per CWC and IMD, the factor responsible for these Kerala floods of 2018 are June-August rainfall 40% above normal. Then during August 1 to 19, around 164% above normal rainfall occurred during this period. Then 35 dams opened simultaneously due to rising water level, and severe August 15 to 17 storm caused widespread flooding in Kerala state. Almost every district of Kerala get flooded during this period, and it was widespread inundation across all the districts. And reservoir operation decision contributed to flood extent. These are the main causes that cited by CWC and IMD. And what lesson we can learn from this Kerala floods? That integrate watershed management with reservoir operation protocols, then deploy near real-time star mapping for situational awareness under cloudy condition, and improve gauge telemetry network, and implement decision support system dashboard. So this photo shows the aerial view of flooding in Kerala, and this is the normal rainfall and actual rainfall in 2018 in Kerala, that is from IMD. Then I am presenting second case study of Kosi, that is embankment bridge that occurred in 2018. And what are the different factor that caused this flood? Before discussing this flood, I will tell you this is the bridge point occurred, and around when river is shifted by 25 kilometers. So in this flood, number of people get died also and get affected also. So what are the key factors during this flood? This event occurred on August 18, 2008, and reached around 113 kilometers upstream of Kosi, barrage in Nepal. River changed course to older channel, approximately 120 kilometers eastward shift. And one important factor in case of Kosi flood, because it was eastward shift. In case of all other river in India, there is westward shift is there, but because due to some location of this watershed on world map, this river is shifting in eastward. Otherwise, all other river in India that shifting westward. So this is one of the important factor in case of this Kosi flood. We must understand. Then in this flood, around 3.3 million people affected in Bihar, and around 3,700 kilometers area get inundated. Around 500 fatalities took place during this flood, and it was widespread destruction of homes and farmland. And for technical or developing new system, what lesson we can learn from this flood? The lesson learned from this flood are continuous embankment health monitoring and effective sediment management are critical in case of flood disaster management. Then transboundary governance and SOPs with Nepal must be strengthened. That is transboundary. We require international cooperation. Then planned reallocation strategies for very high risk zones should be considered. Then we now study case study 3, that is Chennai urban flood, case of urban flood that occurred in December 2015. And what are the different factors as per NIDM and TAG report, control TAG report. During this December 2015 flood, the factors responsible are extreme northeast monsoon rainfall. Around 1049 millimeter rainfall occurred in November 2015. That is highest since 1918. So that rainfall occurred not in 24 hours, but within short period that rainfall occurred. Then stationary cloud on December 1 delivering 490 millimeter rainfall at Tamram in 24 hours. Then urbanization blocked natural drainage system and reduced water retention area. Reservoir release during peak rainfall worsened flood in city areas. Around 500 fatalities and more than 100 billion economical damage occurred during this flood. And what lesson we can learn from this case study? Urban drainage retrofit is necessary. Then restore natural waterways, redesign capacity, remove encroachment from lake, tanks and drainage channels. Then green-blue infrastructure in city is required. Then permeable surfaces and retention areas should be increased in urban settlement. Then local early warning system coupled with reservoir city coordination should be there. Then we will see the case study of Tavi flood, that is Jammu Kashmir flood, because that flood occurred in Jhelum river basin and Tavi basin. I am presenting here case study of hydrologic modeling of hydrologic and hydrologic modeling of Tavi river basin. So this is a Tavi basin and major left bank of tributary of Chenab river. It origins in lap of Kailash Kund glacier and adjoining area southwest of Bhadraba. And this is the extent of this watershed. And this watershed elevation ranges between 239 to 4,331 meter. And basin area is around 2,964 kilometers. So this is the important factor because it's Tavi basin having less than 3,000 kilometer square area, but it produces the discharge more than Krishna river basin. That is, and it is a flashy flood basin. That flash flood occur within 6 hours, 6 to 7 hours after extreme rainfall. So this case study is very important. And climate of this basin is subtropical monsoonal climatic regional. And annual rainfall in this basin is 900 to 1900 millimeter. And this is mesogeographic region north of the Panchal thrust and Panchal thrust to Udhampur thrust and low hill log between Udhampur to Jammu. So this is riverfront, Tavi riverfront area. So this is the three-dimensional dam of this basin, and these are the damages that occurred due to 2014 floods because it is under construction. Barrage get washed during these floods, and in 2020 flood also this bridge also damaged in last year also, and this bridge also that damaged in 2021. So this is very critical location. And this is you can see this this is a damage to the bridge, and this footage we have collected. Our office staff collected this footage of damage to the bridge on his camera. So this is a case of overtopping, and you can see it is a Tavi flood that washed away in 2020. And to understand this different dynamic flood phenomena in Tavi Basin, we have considered climate change modeling, then hydrological modeling, hydraulic modeling, flood mapping, and flood. We suggested some flood mitigation measures in this basin. We did this study for government of Jammu Kashmir, and these are different input data we have used in this study. And we also conducted a design flood because CWC used unit hydrograph techniques, and we also use this unit hydrograph technique to generate this map for 2014. And this is a synthetic unit hydrograph method recommended in CWC's flood estimation report for Western Himalaya Zone 7. Has been used to estimate design flood hydrograph for 50 and 100-year return period. And this is a flood map of 100-year return period. And by this unit hydrograph, we estimated time to peak was 8 hours, and estimated time base of unit hydrograph was 18.94 hours. This estimate of time to peak and time base of unit hydrograph can also be verified from generated discharge hydrograph from observed hourly stage value by CWC for high flood that occurred in Tavi during 4 to 6 September 2014. Because in 2024, flood of 100-year return flood occurred, and we get chance to verify this unit hydrograph theory and actual hydrograph. This is a hydrograph generated by using unit hydrograph theory, and I will show the actual hydrograph. So this is hydraulic modeling framework. Basically, we have used unsteady state modeling in this study because the unsteady flow component uses a numerical solution of complete equation of gradually varying unsteady flow, and commonly referred to dynamic wave equations. The sentiment equations used to simulate unsteady flow are more physically correct than energy equation, which is used to simulate steady flow. So in this model, we are using steady state, and this is the case we studied first, this hydrodynamic model for Tavi River front, and this Tavi River front is going on. You can check website. So around 3.7 kilometer work is already done, and around 7 kilometer work is remaining, that is going on. And we did consultancy study for this study area. And in this case, what we found that the geometry file with cross section and bridge and barrages information we have used in this study. In case of Tavi, it is mostly assumed that 65% and 35% flow bifurcate in Niki Tavi and Wadi Tavi, respectively, without consideration of the splitting junction. Because in previous study, they are using such a type of bifurcation, 65% in Niki Tavi and 35% in Wadi Tavi. In case of Dogra language, Niki means small river, and Wadi means big rivers. But over period of time, due to sedimentation, now Niki Tavi become big river and Wadi Tavi river become small river. And when we use dynamic modeling option, then we found that around 71% going in Niki Tavi and 28% flow is going in Wadi Tavi. So these are the some result of our modeling, and this is the footage of 6 September 2014. This is actual footage, and you can see that in between these two bridges, our simulation result and actual field photograph, which we used for calibration. And as I told, because this catchment, this river basin have a catchment area around less than 3,000, but the recorded highest flood was 13,565 cubic. That is even more than river basin having catchment area more than 40,000 also. You can check. And by using this actual footage, we found that for this river reach, the managed reference coefficient calibrated is 0.022 by using different sensitivity analysis. This is again actual flood footage, and we have used this flood footage in calibrating and validating our hydrologic and hydraulic model. And this is our actual model, HECRAS 1D model. And actually what we are identifying, because already I have shown one picture to you. In 2014 flood, under construction barrage get damaged, and in our hydraulic modeling study also, we get why this under construction barrage get damaged, and we get exactly great region why this thing happen. And you can see this region in this animation. So actually this is barrage. So here you can see that water force is in this direction, and also flood out of this under construction pillars, so that get washed out, and also erosion also causing in this area also, because there is high flood velocity in this area. And why what we understood from these studies, the estimated flow bifurcation ratio for different design flood condition ranges between 70 to 73%, with average of 71%, and 29.82 to 26.99%, with average of 28% of the total flood at the junction for Nikitavi and Vaditavi by doing dynamic modeling. Then we tried to simulate this flood. We have daily rainfall from IMD data, and in this basin we have used, this is grid data, 0.25 grid data from IMD, and this is actual IMD point measure data and IMD grid data, and both these data are matching. You can see here how these data are matching at different stations. So we verified this IMD grid data and actual data also. Then we have two rain gauge data at Chatta at Jammu and Kawa at Udhampur. So we tried to use this bivariate satellite ratio disaggregation method to convert this daily rainfall data into hourly rainfall data at different different subbasins. We divided this subbasin into 9 subbasins, 14 subbasins, and we generated by using this bivariate satellite ratio disaggregation method to convert daily data into hourly data. And these are the results. This is 2014 case, and we are able to calibrated this observer hydrograph and HECHMS simulated hydrograph at Sidra at Jammu, Udhampur, and Talmai Bridge, Udhampur, and Jammu, Bikram Chowk. And here you can see how we are able to simulate this map accurately. And if you remember, the hydrograph generated by using unit hydrograph techniques and actual simulated hydrograph or observer hydrograph are similar. So we are able to compare this unit hydrograph technology with actual observations and simulation of HMS. So from this point of view, this case study is very important. Then we validated this for 2021, and then we set up downstream of Jammu, this Sidra site is here. We set up this HECRAS model, 1D and 2D models, and these are the some Landsat images. So here this from these Landsat images, we can get inundated extent from this map, and we don't have the actual flood depth estimation. So we went, collected these pictures, and from this picture we went at ground level, and we measured flood depth that required to validate our model. And this is a flood hazard map, 100-year return flood, and this is from our HMS and HECRAS study. And what we found that around 67 villages get flooded during these floods. This is our model results, and this is actual map with flood depth. So we got depth from 0.3 meter to 13 meter depth in different areas, and we prepared this hazard map. We presented some important places on this map, and this is the actual observed data collected by flood department of Jammu Kashmir. And according to their information, it is written that they have found that around 66 villages get affected, and our study shows that 67 villages are got affected during this flood. So our modeling study result and actual data is matching very much. So what we conclude from these studies, based on the presented various performance evaluation criteria, the performance of HMS model during calibration and validation of Tavi River Basin up to Jammu gauging station is considered very good at Jammu and Sidra gauging station for simulation of discharge and stage hydrograph. However, for Udhampur gauging station, it is considered a good model performance. The calibrated HMS model for Tavi River Basin up to Jammu can be confidently used for flood inundation mapping under climate change. And this is particularly flash flood case study. And this modeling framework is working very fine. Then comparison of flood inundation depth map by HECRAS for the lower Tavi River Basin with photographs from the campus of Seri Kashmir University of Agriculture Sciences and Technology of Jammu suggests that the flood inundation depth at the campus is around 35 centimeter from the photograph, and those from HECRAS was around 44 to 60 centimeter. So here also we are getting very close to this actual observation. For the September 2014 high flood event, the total flood inundated area computed in the lower Tavi Basin based on HECRAS simulated flood inundation map is about 22,251 hectares, out of which around 12,000 hectares lies in India and another area in Pakistan. And final concluding remark is increasing trend in number of heavy rainy days is predicted by all the models across basin in the range 15 to 35%. The total annual precipitation is also expected to increase in the range of 15 to 35%. Hence, for future flood assessment, the historical observation could be perturbed in this range. So this is most important concluding remark we got from this study. Then I am going to present this case study of Brahmani Baitani River Basin. This is a case study of coastal flood inundation mapping using ADSL and SWAN and two-dimensional HECRAS model. Here we used a forecasting the tidal effect, sea surges at the river ocean confluence in the Bay of Bengal. So this is the study area, And this is the study area on northwest Bay of Bengal we have taken to calibrate and validate our ocean models, ADSR and SWAN model. And this is the bathymetry data we used in this study. This is overall methodology. So for ocean wave modeling, we are using ADSR and SWAN. Then flood modeling framework, we are using hydrologic and hydraulic modeling. And then we are generating coastal flood inundation map. And for validating this map, we are using Sentinel and other data. So this is mathematical equation used in ocean modeling like ADSR and SWAN. Basically, this ADSR and SWAN model use these very detailed equations, and our sentiment equation are specific case of this Navier-Stokes equation. These equations are called as Navier-Stokes equations. So these are different equations used in ADSR and SWAN modeling, and this is the how we generated this mesh to run this ocean model. And this is the result, spatial distribution of simulated wind vector and pressure field over the study region during cyclone Fanny, and that occurred during 3rd May 2019 for different dates. Actually, we are showing this result for 3rd May 2019 at 8 o'clock, 11 o'clock, 3 p.m. and 6 p.m. And this is actual simulations of ADSR and SWAN model, and this is satellite picture. And in this study, we are able to track actual satellite actual track given by IMD. So we verified this result with actual data also. You can see from satellite also. This is satellite image and actual image I also presented by simulation. So these images are matching during these images I shown for Ya cyclone of 2021, and this is a modeling framework we have used for this study. And in this study, hydraulic study, because in this case we are considering coastal flooding also, reservoir operation, then hydrology and hydraulic modeling also, and it is two-way interaction. Because
excuse me, sir, your screen is not visible.
Now it is visible. Hello.
Yes,
Hello.
sir. Now it is visible. It is visible now, sir.
Now,
Yeah.
now it is visible.
Yes, sir. It is now visible. Please go ahead, sir.
How much time I have left?
Sir, you may wind up maybe in 15-20 minutes if you want.
10 minutes. I will take 10 minutes only. 10, 15
Yeah,
minutes.
yeah, yeah. No, no problem, sir.
Okay.
Yeah, thank you.
So this is results of integrated ADSR SWAN HECRAS 2D flood inundation modeling. And here you can see that we got very good accuracy in this case. when we compare class 2D result with SAR data. So around 15% accuracy error in case of flooded area, and less than 3.5% error we got in case of non-flooded area. So it is very good accuracy we can consider. And we can make conclusion from these studies. Flood inundation mapping in lower elevation zone close to coastal boundary require inclusion of tidal height coming from ocean and entering into the river stream. Flood inundation computed from Hecla's 2D model as a combined effect of storm stride, upstream discharges, and rainfall could reproduce the benchmark SAR-based flooding extent. During the cyclone Yas, the maximum flood depth and flooding area in the Brahmani-Paithani Delta, as simulated by the Hecla's 2D model, were 8 meter and 1964 kilometer square. Around 20% of total area get flooded during this cyclone. So, how much these cyclone floods are so important? Because it is not riverine flood, but it is cyclone flood, and around 20% area of this Brahmani-Paithani basin, because delta region is around 10,000 kilometers. So around 2,000 kilometer area get flooded due to this Yas cyclone. And when we use this reservoir operation in properly, then we can reduce this area very significantly, because we have this study, but due to the shortage of time, I have not shown this case study. Maybe next time I will show that. But this shows how much important to include ocean modeling in our flood inundation mapping that I want to show from this case study. Then from the after this case studies, now what system we require to reduce this flood risk in India, we will discuss in this next slide. Then from this all the case studies, we can get some what typical failure modes in India. So one of the typical failure mode in India is infrastructure failure. And what causes are poorly maintained embankments, aging dams, inadequate urban drainage system, leading to catastrophic breaches and flash flooding. And what local solution we can give is remote sensing monitoring for embankment health, standardized maintenance schedules, predictive analytics for critical infrastructure. Then another failure is data and telemetry gap, because we have sparse gauging network, low uptime, delayed reporting, and insufficient real-time monitoring of critical parameters. What solution we can give for this current gap is we can develop IoT sensor network, then satellite-based monitoring system, then public-private partnership for expanded telemetry coverage we can develop. Then in case of India, we have institutional fragmentations, and that is one of the biggest challenge before us, because for managing flood or any kind of disaster, there is good coordination between different institutions is very important. But this is biggest challenge in India in coordinating challenges between state and central agencies, district authorities, and watershed management organization. What local solution we can offer is unified emergency operation centers with clear SOPs or joint training exercise, integrated basin management approaches we can develop. We require research in this direction also. Then encroachment and floodplain losses. Again, this is one of the challenge in our country, because rapid urbanization is there. Due to this rapid urbanization in natural drainage path, it causes hindrance to this natural flow. Then wetland degradation and weak enforcement of land use regulation. This is the biggest challenges. But what local solution we can provide is evidence-based flood zone mapping, strict zoning enforcement, incentives for managed retreat from high-risk areas. That's some solution we can give. Then what advances in science and operation we can utilize, because presently we have Sentinel-1 data, which is near real-time inundation mapping under cloud cover, providing all-weather flood extent monitoring during monsoon season. Also, we have NISAR data also. That is high-resolution data currently we can use. Then we can use cloud platform like Google Earth Engine. That Google Earth Engine enable rapid flood mapping workflow and historic change analysis without requiring local computational resources. Then we have AI techniques like machine learning and hybrid models, AI enhanced short-term forecasting and nowcasting, transforming from research to operational pilot at city and district level we can undertake. And then we can use global services like GloFast. And this is different technologies, key advantage and maturity in India. Like Sentinel-1 SAR data, it is all-weather capability, and it is operational in India now. Then Google Earth Engine, rapid mapping, growing adaptation in India. Then machine learning forecasting, local prediction, it is in pilot phase. And GloFast basin scale alert, it is in use in India. So operational pilots, district level integration of SAR mapping with local gauging network shows promising result, as I shown in CWC flood forecasting case. Then recommended technical architecture is, because in case of disaster management, we require data sources, because if our input data is good, then our output also, or our strategy is also good. So we require to develop some good data sources and their management. So whatever different data sources are, meteorological data like IMD rainfall, temperature, weather forecast, these are very important data for disaster management. Then hydrological data like CWC, river gauge levels, discharge and reservoir level, that data we require for flood management. Then satellite imaging like NRC, optical imagery, Sentinel-1 SAR, or all-weather mapping, or NISAR data presently available, we can use this data also. Then crowdsourced information like local communities, social media for ground truthing. This information very important, because in case of Tali, I have shown that how social media or images we can use to calibrate and validate our model. Then there are different processing layers like data assimilation, that is integration of diverse data streams into unified platform. Then hydrologic models like simulating river flow, water level, inundation extent. In case of India, we majorly use HMS or SWAT model, but in case of flash flood or rapid flood, we require some national hydrological models that can be utilized at for diverse situation. So central agency working with this direction, already working in this direction. Then as AI techniques are using increasing day by day, so machine learning tools we can use to predict, because in case of meteorological and hydrological data, there is different kind of noise is there. So we can use these machine learning techniques or deep learning tools to remove noise and increase our forecast accuracy. That is refinement and nowcasting. We can use these ML tools with hydrologic and hydraulic models. Then SAR inundation mapper, we can generate automated workflow on GE for rapid SAR processing. And we have developed such kind of SAR mapper, and maybe after 2-3 months we will host this mapper on website. And these are different dissemination agencies in India, like Central State Early Warning System, centralized platform for generating and issuing warning, district dashboard, localized dashboard with real-time information and decision tools. Then SMS voice alert, automated alert to register user in the threatened area we can generate. Then community volunteers, local network for receiving and disseminating this alert is that is this multi-tier system emphasizes decision support dashboard for critical action like reservoir operation and evacuation planning. And for operational disaster risk management process, this is the sequential flow from detection to post-event assessment. Like detection, for detection we require IMD rainfall data, radar, gauge and satellite SAR data. Then we use forecast like hydrologic models and EML short-term nowcast. Then access like SAR plus model inundation map. Then based on this SAR and model inundation map, we decide on evacuation, reservoir operation, or deploying different asset like NDRF or SDRF teams. Then notify DSS to state, district and community. Then we can plan to respond activity like rescue, medical, relief distribution, and access impact response and effectiveness. And we can learn some lessons from these events also. So decision point like attach trigger feature to each decision box and predefined SOPs. Agencies roles in India like CWC, State Disaster Management Authority, district collectors, National Disaster Response Force like NDRF, SDRF. We must define the different agency role. Then multi-channel warning like SMS, voice alert, community volunteers, local media, signers and mobile apps. We can generate workflow, how to give warning in multi-channels. Then continuous improvement because already we increasing our technological know-how, but our challenges are increasing day by day. So in case of disaster management, any kind of disaster management, continuous improvement is one of the key. Post-event assessment update SOPs and improve future preparedness. So in short, IMD from IMD we got meteorological data, from CWC hydrological data, MRC we take SAR imagery, National Disaster Management Authority, that agency very important for national coordination, and NDRF response operation for actual operation. This is very important. So we require very much coordination between these key agencies. Then what is the disaster reduction goal in Millennium Development Goal? Because presently we have Sustainable Development Goal, but we must understand what are the goals that during Millennium goals. Why not now? So no reliable damage data, no clear roadmap to reach the goals. So what this sentence telling is that we require reliable damage data and clear roadmap to reach our the goal. An alternative goal: the number of communities, municipalities which satisfy a certain standard on disaster preparedness. So that data is also important. So according to the Hugo framework for action, priority for action, first is ensure that disaster risk reduction is a national and local priority with strong institutional basis for implementation. Identify, access and monitor disaster risk and enhance early warning. Use knowledge, innovations and education to build a culture of safety and resilience at all levels. Reduce the underlying risk factors and strengthen disaster preparedness for effective response at all levels. So these are the priority area during this Hugo framework that accepted by UN in 2015. And as I told, strong institutional basis for disaster preparedness is very much important because it is necessary to establish a common mechanism by which a community is encouraged, is directed, and learn each other to take a rational procedure to make themselves prepared for warning, information, dissemination, evacuation, refugee sheltering, refugee support, recovery, receiving official and voluntary help, etc. So, design principle of disaster preparedness are designed according to the local reality. So for each local problem, we require local solution. So designed according to the local reality and manageable within the local context and administrative framework. Decided, implemented, checked, and revised by the community authorities regularly, and have a built-in mechanism for continuous improvement in a positive spiral based on a plan do check action cycle, linked with and consistent with the national and regional emergency management scheme, supported by the best practicable disaster forecasting system available to the nation and region, internally and externally reviewed and checked regularly, and licensing procedures should be built in and evolve with societal change such as land use change. Then design step of local flood disaster preparedness are form a community flood defense committee and identify the goal, design a set of rules of procedure to reach the goal, identify the annual objective for improvement, plan and materialize the administrative, technical, and financial action to achieve the annual objectives, establish a linkage with the national state level administration, and prepare for internal and external review process and licensing of this ISO. So I am skipping these slides. In case after this preparedness, we require actual solutions. So presently there is some natural based and structural mitigation measure we can suggest for this different area, like floodplain restoration, reconnecting river with natural floodplain, wetland restoration, and mangrove conservation in coastal areas, provides natural flood storage and peak flow reductions in this floodplain area. Then retention and overflow system, retention basin, overflow channels, and controlled setback levees create a buffer zone for peak flow management while protecting critical infrastructures. And there is another concept of urban green infrastructure. You can see in this picture also, adjoining picture also. Urban green corridors, permeable surfaces, and stormwater retention system improve urban infiltration and reduce the runoff during intense rainfall events. So, what is our benefit? That is of these nature-based solutions are biodiversity enhancement, groundwater recharge, carbon sequestration, and urban heat mitigation alongside flood risk reductions. And this is a system they use to check the leakage of levee, that is levee management. So I also involved me in this practice in Japan. So I have shown here. I doesn't seen this practice in India, so I want to show this to all of you. Then in case of capacity building and community engagement, community drills and risk mapping, participating risk mapping at village level, identify vulnerable areas and safe zones. Regular community drills ensure preparedness through the practice response procedures. Then volunteer network and alert system. In case of volunteer network, local volunteer cadres trained in early warning dissemination and first response, multi-channel alert via SMS, IVR, community radio, and local announcement in regional languages. Technical training program, specialized training for operators, district officials, and emergency operation centers focus on decision making under uncertainty and coordination response protocol. And one thing I understand that because technical advancement is necessary, but for managing disaster and reduce risk, this capacity building and community engagement is very important, and that component we are missing in India. But recently, now community drills are conducted by National Disaster Management Authority. So because India also identified capacity building and community engagement is most important factor in risk reduction due to this flood disaster or any kind of disaster. So we must conduct research in this area also. So this is implementation roadmap. for 0 to 5 years, like foundational improvement like audit existing hydrological sensor, install telemetry at strategic location, pilot integration into early warning system, then scaling operation like expand early warning flood warning system to major basins, deploy urban decision support system in priority cities, standardized data sharing protocols, and for 3 to 5 years, advanced integration like integrate machine learning forecasting capability, implement NRSC operational product, strengthen community resilience, and outcome will be the integrated flood management system for any cities or basin. Then one of the most important part is monitoring and KPIs. If KPI is the key performance indicator to guide investment decision and access flood risk management effectiveness. Like in case of gauge uptime percentage of time critical hydrological and meteorological gauge are operational and transmitting data reliably, indicate the health of data collection infrastructure, like accuracy of inundation map, percentage accuracy of flood inundation map validated against ground truth data or independent satellite imagery. This measures the reliability of mapping technologies. Then early warning system lead times in hours, average time between issuance of flood warning and actual onset of flood events. And this indicator longer lead time allow for better preparedness. Then evacuation compliance rate, percentage of population in high risk area that successfully evacuate period to flood events, and this indicator reflects effectiveness of warning disseminations. Regular reporting on these KPIs provide critical insight for adaptive management and strategic resources allocations. So only one slide is left. This is way forward. Develop system for reservoir inflow forecasting based on rainfall forecasting. Review, develop rule curve, particularly for reservoir with live storage capacity of greater than 200 MCM for multi-purpose regulation. Practice integrated real-time operation of reservoir at basin scale, considering system while taking decisions. Then implementation of flood plain zoning, remove encroachment from rivers and restore their flow carrying capacity. Release one flood dose every year to establish right way of river. Provide more opportunity to water to infiltrate and create flood detention areas, and create organization for river basin wide planning and management, including flood regulations. So thank you very much. If you have any question, you can ask me now.
Thank you, sir. Very nice presentation. And a lot of the aspects here has been covered and the case studies. Um, Candidates, if you have the participants, if you have the any questions, you may unmute yourself and ask, sir.
Good evening, sir.
Good evening.
Sir, very nice presentation. A lot to learn.
Thank you.
Sir, I have a couple of questions.
Yes.
First of all, due to global warming and climate change, maybe discharge rate of different rivers, especially perennial rivers, may change. Now, sir, you have shown that you were using some model to predict discharge rate and also to predict the future floods. Sir, is it also considered that the discharges is also increasing and it may also, to some extent, may increase the percentage of flood in future?
Yes, I will answer this. It is very important question, and I have shown one slide is there. As per recent IPCC report, in India, that peak rainfall is going to increase by 15 to 35%, and it is in different bases. But most important part is our rainfall intensity is going to increase at a very high rate. Like previously, suppose when 100 millimeter rainfall occurring in 24 hours, but that rainfall now occurring in within 3 hours. That is the major problem, because we have seen one case study of Chennai flood, So around 400 millimeter rainfall occurred in 24 hours. And as per the case of definition of extreme rainfall, when rainfall greater than 10 centimeter, that is 100 millimeter, that is 400 in 1 hours that took place. When more than 10 centimeter rainfall occurring that 1 hour, we call it is a extreme rainfall. But around 1400 millimeter rainfall occurring that period, so that is our main problem, how to manage flood disaster. Because when such a high event occurring in very short period, we get very less time for preparedness. And there is one another report of Ministry of Earth Sciences. Last year uh, uh, they have one final report on Ministry of Earth Sciences, and they also considering in India the uh, extreme rainfall event will increase by 15 to 35%, and they have given in which basis how much increase will be there. And another question you have asked whether I have considered this increase in our study. Yes, we have used different climate change models, and we converted this data, daily data, in hourly data using some hourly record, because in most of the case we have daily data, and this rainfall event occurred in very short period. So we require tools to convert this daily data into hourly data. Then we can compare the changes in hourly data, how intensity of different event is increasing. So yes, we have considered this. In case of Tavi, we consider taken into account different climate change models, and we have used this hourly data, converted data for 2014 flood, and we have scaled this hourly events to see the impact of increasing rainfall intensity. So I have complete report. If I want, I can share that report. How to consider this high intensity, extreme intensity data under climate change in our inhalation mapping and modeling also. I think I have given answer of your question. Hello.
Yes, sir. Yes, sir. Sure, sir.
Okay. Thank you very much.
Thank you, sir.
Yeah, participants, if you have any question, you may later on also you can write to us, and we'll forward to sir. And if you have any queries, okay, sir. Yeah, Robin sir.
Yeah, nice presentation, sir. Thank you.
Thank you, sir. Thank you,
Thank
sir.
you for sparing your time. A couple of questions from my side. Suppose we are doing a, some bridge vulnerability against the flood. Okay, so is it possible to get that flow maximum high flood level of the bridge? Suppose it is already constructed. So given the location, is it possible to get the flood maximum that can come due to this? As you said, this climate change and all, it is every year increasing. So the flood, this river directions are all changing. So is it really possible to model and then get it?
Yes, sir. Because thank you for this question, sir. Actually, in case of Tavi River, we did consultancy for Jammu Kashmir, and
Yes.
we have provided a result with millimeter accuracy, some centimeter accuracy.
Yes.
Because this HECRAS model, if we collect data from ground and we calibrate our model, then our model results are actually matching with actually in the ground.
Okay.
So that because we warn government that this bridge will wash if such event happen, and I have shown one footage to you.
Yeah.
and actually this damage occurred.
Uh-huh.
So by using this HECRAS and all model are now very mature,
Okay.
and for accurate estimation we can use this model. Another model that is Mike 11 and Tuplo. That model also we can use for real time operation also.
Okay. So it is possible. So
It is
another,
possible, sir,
yeah,
because
yeah,
at number of places we use this. Now we are doing one study for Surat city, and actually we designing some channel and designing flood pumping station. So in that case, we are considering some centimeter accuracy. Then,
oh,
so tools are very advanced now. If we have very good data, then we can get very accurate results, sir.
yes, yes. So maybe we will contact you. We have some
Yes, sir.
requirements, so that it can be your data will be your environment. We can include in this work.
And another information, sir, I have shown one slide to you that data of ocean storm surge.
Mhm.
That data collected at 2-minute interval,
Okay.
and our model is able to match this observed data with around 92% efficiency.
Okay.
And because we have considered very big area, na,
Mm.
total Bay of Bengal area,
Mm.
and we are able to simulate this result not only for one event. We have considered the event from 2013 to 2024 for this
Mm.
study.
Mm.
So in all event we are able to produce good results. So now I can say that yes, we can simulate this result with much confidence.
Okay. Then one more question is on that this one is flash flood, another is that cloud burst.
Yes, sir.
So this cloud burst, is it? Have you done any time this?
Sir, we are working on cloudburst. But in case of cloudburst, what is the problem, na? Presently, because I have said that we are using WRF because national. So there is one center in Noida, national shortwave center is there of Ministry of Earth Sciences, under Ministry of Earth Sciences, and another is IIT of Pune, Indian Institute of Technology Meteorology. They are working on WRF model. So they have now created data at 12-meter grid size. But that cloudburst, for cloudburst, it is very difficult to predict that cloudburst, even if we are having data at 3-kilometer grid size.
Okay.
We required grid size less than 1 kilometer.
Oh.
So it is computationally very heavy, and we are at NIH, we are doing study for Himalayan region at some spot. We are running this WRF model for grid size less than 1 kilometer or 1 kilometer.
Okay. So maybe in future it will be.
Yes, sir. Because IITM and Noida Center is working and they are getting good results. So in near future, we can able to predict this cloudburst with much accuracy
Okay.
than which we can present presently.
Thank you, sir, for your kind uh, 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 this involvement. So over to Sushanta.
Yeah. Thank you, sir. Thank you for accepting our invitation. It was very informative session. And sir, we would like to present you a small token of thanks, sir, from our side. Please accept it.
Okay, thank you, Professor Susanta. And I am thankful to you and Robinson also and all participants for listening me and providing me this opportunity to deliver this lecture before all of you.
So
It is my
pleasure is
pleasure.
all ours, sir.
And another thing, I am able to finish my talk within given time, up
Yes,
to
yes.
7:30.
Yes, sir. Yes, sir. Thank you again, sir. We'll look forward for your in future more talk about this topic, sir. Thank you.
Okay.
We'll be in
Thank
touch.
you very much.
Yeah, I'll be in touch with
Okay.
you.
Okay.
Sir, you
Thank
may
you.
end. Yeah, thank you, sir. You may end up the meeting, sir. You may leave the
Okay.
meeting.
Thank you.
We'll start the next session. Thank you, sir.
Okay.
Thank you, sir.